Hello ladies and gentlemen, thanks for tuning in again today. This is the 7th lab of GGS 300, Quantitative Methods for Spatial Science. Today I'm going to be covering a variety of different tests that we covered theoretically within the lectures, and I'm going to be providing you both manual and automated calculations for those different tests. And hopefully this is going to complement what we learned in the lectures by showing you how to actually implement the kind of more theoretical and abstract concepts that we implemented within the previous class material. So I hope you've been able to watch those lectures, and today I hope you've been able to download the code, and then hopefully you can run that in tandem with watching the video and really improve your understanding of these few key tests. So we're going to be covering two sample difference of means tests, and we'll be covering a parametric version of that, so the t-test, and also the Wilcoxon rank sum test for the non-parametric approach. And then we've got matched pairs difference tests. So up here, these were independent samples, whereas down here we have dependent samples. So for example, where we might sample over two different time periods, but they're the same entities which are being sampled. And essentially we have a parametric approach to test here, which is the matched t-test. And then we have a non-parametric approach, which is using the Wilcoxon matched pairs signed ranks test. And then finally, we're going to quickly close by just covering the two sample difference of proportions test, which we're not going to calculate manually. We're going to use one of the inbuilt tests within R to estimate the test statistic for that particular set of data. Okay, so without much further ado, let's begin and let's move on to the two sample difference of means. So imagine that we have data showing poverty rates by state for three different time periods, so the year 2000, the year 2010, the year 2012. And the states essentially are categorized into one of four geographical regions, which I'll show you in a second. It's hypothesized that the West of the United States, given the fact in many cases it's got a very booming tech industry, as a consequence there would be lower potential poverty rates when compared to the southern states in the US. So the question is this true? So obviously our hypothesis there is one-sided. We think that the rates the rates are essentially lower in the south, so we're going to be looking in the lower part of the tail of the distribution. So that's essentially what we want to go out and try and find. So first of all, we need to load in the data that we've got, and you'll remember previously I gave you this little snippet of code, and that code essentially just finds the folder in which you're running this R code from, and providing the data is in the same folder, you should then be able to obtain this folder path and then set it as the working directory, which allows you to then just import the data really easily. So what's this doing is basically taking the directory name that's returned when you get the path from the RStudio API, so the application programming interface for the source editor. And essentially what that yields, if we run this, is the path to where my current R code is. So it's in 300 quant methods, fall 2020, week 9 lab. And I'm able to set that as my working folder. So hopefully that's not new to you and you're familiar with that already, as we've covered it in previous labs. So let's load in the data now, and I've given you a text file, and within that text file you've got poverty data for all of the states for three different sample periods. And essentially what we're able to do is we're able to subset out those rows that are equal to specific specific conditions that we give them. Okay, so what I'm doing here is I'm saying go into the poverty data, go into the year 2012, and if the region is equal to W for West, then subset it into West poverty. Okay, so when we do that, all of the variable data is stored in this vector here, as you can see. We can do the same now for S poverty, so South poverty, which subsets that too. So you've got another vector here of all of those data And essentially you can look at the summary. So we've got a mean poverty rate for the states in the West of 13.87, so 13.8%. Whereas in the southern states, the poverty rate is about 16.9%. So it is actually higher in terms of the average that you're looking at here. We can plot that data. So these are on the same scale. They're running between 8% and 22% as the rate. The difference is that for the West, we do have more states in the lower end of the distribution here, whereas if we look at the South, we do have more states in the upper end of the distribution over here to the right. So that should be indicative of potentially what we may find. So how do we work out the t-test by hand first? So essentially our null hypothesis is that the mean poverty rate by state in the West region is the same as in the South. Okay, so we don't expect there to be any difference. Whereas the alternative hypothesis is that the mean poverty rate in the West, for example, California and the surrounding states, is essentially lower than in the southern region that may contain places like Alabama, where the poverty rate is generally higher. So we can state that explicitly. So if you look for the null hypothesis here, it would be that x bar from the West sample and the southern sample are essentially equal. Whereas the alternative hypothesis is that the x bar, so the mean value in the West, is lower than the mean value in the South. Now that we've stated those hypotheses, we can define the test. So we need the number of samples to determine the test. And we need to, so let's get all the stats that are required. So we have these vectors already for the West and the South. All we're doing here to obtain the number of samples is using the length call. So it's just looking at how long the vector is. So it's saying like, how many individual entries do you have? Over here you can see already it's actually stating it's from 1 up to 13 data points. So when you enter N1 using the length call, you get 13 here. So that shouldn't be too unknown to you. I think we may have used this in the previous class. We definitely took the mean in the previous class, and we definitely took the standard deviation in the previous class using those inbuilt functions. So I hope that that's fairly self-explanatory to you now. So let me just go and find the math equation. Well, this is what we're trying to calculate for the two sample difference of means test. So we want either the z or the t statistic, depending on the size of the data sample that we have. And what we're trying to calculate now is the x1 bar and the x bar 2. So these values here. Both sample sizes are not over 30. So you see we've got both of them are lower than we would like. So we're better off using a t-distribution and t-test approach. In general, it's best to use the t-test anyway, as we generally don't always know the population parameters for variance. We do need to state what the level of significance is that we're interested in. So we want to be 95% sure that the results don't occur by chance. So we're going to state an alpha value of 0.05%, which provides us with that 95% certainty. We also need to get the number of degrees of freedom. The degrees of freedom is always the number of samples in the data sample with one subtracted from it. Here we're adding together two samples, and therefore we're subtracting 2 from it to get the number of degrees of freedom. And when we do that, we get 28 for the number of data samples that we've got. So that's essentially 13 plus 17 minus 2, 28. Then we need to find the critical value for the alpha that we've got, which is minus 1.70 here. So we can take the t-critical value and we can plot it using the type of curve that we did in the previous week. And essentially for that value that we've got, what we're saying is for the samples essentially to be categorized as being significantly different, and for us to be 95% confident that we can't actually reject the null hypothesis, we would need that sample mean to be within this red area over here. And I hope that by graphically doing that, that helps you understand the point of having this critical value. So this point at which after that threshold has been crossed, we know that then the sample is in this critical area where we can reject the null hypothesis. So let's calculate the test statistic now. So we're going to use the SVE, the separate variance estimate, as stated in the book. We covered this already within the lecture, so this is the calculation that we want here. So we need to take the square root of the summation of these two different divisions. So essentially what we're doing here is we're taking the square of S1, dividing it by the number of samples in that first sample. And then we're taking the square of S2 and we're dividing it by the number of samples within that sample. And then we're taking the square root of that. And that's how we get the SE. So it's the standard error of the differences between the means, okay? So when we do that, we get a value of 1.196. So essentially this is accounting for the level of difference that we would expect to happen by chance just by taking random samples. And then what we need to do is we need to take the x bar 1, the x bar 2 values that we've already calculated and divide it by this standard error. So essentially this is the difference between the samples as the numerator on the top half, and then the standard error, the difference between the means, as the denominator on the bottom half. And that provides us with our t-value, which is significantly exceeding the critical value which we set. So our t statistic is larger than the magnitude of the critical value. So we reject the null hypothesis at the 95% confidence level. So essentially, we found evidence that makes us believe that the West region has a lower poverty rate than the South region, given the data that we've got and the significance the significance level that we set exogenously, which is pretty much always 95% because that's the standard approach within the literature. Okay, so that's how we did it manually. Now let's just play around with how we do that and generate that value using the automated inbuilt R functions. So if we get the p-value for that result t, it's actually 0.0085, so it's really quite low. But we're able to compare that p-value that we got from the manual calculation to the p-value that we get from using the inbuilt t-test function. So essentially when we do that, we get a very similar p-value just down here. And if you want to look more at that student t-test function, then I suggest you type help into the R menu and you take a look here at the description, the usage of this particular function that enables us to just automatically generate the results rather than going through all of the manual calculation which we did above. Great, so I think that that's pretty much everything for generating the parametric approach to testing the difference between two samples. Now let's focus on the non-parametric test. So maybe the data that we have are too small in number to use a parametric test reliably. Maybe the data don't come from normally distributed population. Maybe the data are ordinal rather than continuous, so interval or ratio, and therefore we have to look at a test that can account for this. So by using the Wilcoxon rank sum test, we're able to deal with these shortcomings that we may have. So firstly, we'll need to actually rank the data. We need to put all of the values in a single vector, and we need to be able to identify the difference between the values. So essentially what I'm going to do here is I'm going to create a data frame called values that you're able to look at. So we have the class, which is the region basically, so whether it's from the west or the south, and then we have the poverty rate just here in the prop column. So what we've done is we've said create me a vector which has the word west repeated the number of times that n1 is in length, because that's the sample, and then repeat that as well, just repeat that number for the second sample as well. So it's just literally providing these classes, and then we're able to combine these two together. So when we combine the class and the data that we've got, this is how we end up with the values data frame. Okay, so hopefully that's clear to you. Now we're able to actually allocate the ranks. So what we want to do is we want to rank all of the data based on the values that are there, and we want to put it into a data frame so we're able to inspect it nicely. And this just allows you to then look at the different data columns and play around with what's there. So you can see we've got the regional class here, we've got the poverty rate, and then we've got the ranks that have been allocated. So if you click on the top of the row, you should be able to rank all of the data depending on which variable you're interested in. So here, if we sort it based on the rank, we can see we go from 1 all the way down to 30 in rank order, and we can see that this corresponds with the magnitude of the poverty rate. So I hope, given the fact that we went over this in quite an abstract and high-level way in the lecture, that this provides you with a bit of understanding now as to how we need to combine those data sets together and start to allocate a ranking variable. Great, so now that we've done that, we can actually just separate out those metrics, so those rows that we are interested in for the specific regions. So here we have the combined data frame. This is all of our data, and what we're saying is subset, which basically is, in this case, it's the name of the data frame, and then you open using a square bracket, and then what we're saying is give me all of the rows. So that's what the comma means, give me all the rows where the class is equal to West. And when you do that, you end up with this subset of rows just here. So all you've done is say make a new data frame called West, which contains only those rows which are part of the West class. And that's got all of our poverty rate data and the ranks for that particular region. Okay, and we can do the same for the South. So I hope you're able to do that and you understand exactly what we've done. If it's not clear, break it down to a smaller problem, run it on your own machine, and look at the results that are produced. Once we've got them separated out, then it's really easy for us just to sum. So we can sum all of the ranks in West and South to get the W1 and W2 variables. So here we are. This is the Wilcoxon rank sum test. This is what we're interested in, the sum of the ranks for each sample, so WI, in this case W1, W2. And then we want the mean of the ranks for WI, and we also want the standard deviation of W. So that's what we need to get next. So to get the W1 bar, we basically need to follow this equation down here. So we need to input the number of data samples for that one sample of interest, and then run through this calculation, and we're able to produce this value of 201.5. And then we need to get the standard deviation of the W, so we need this equation down here on the bottom right hand side of the slide. You can see that it should be reasonably easy to input this data. It's not too complicated. You just need to make sure that you've got the N1 and N2 values, and then you're able to generate the metric of interest here. So the standard deviation, which is 23.8. Then hopefully you can allocate that into your global environment to get the SW. And then you've got all of the components which require you to actually calculate the test statistic. So hopefully now we've got the W1. So this here, WI. Let's do this for the first sample. We need to subtract W1 bar as we've done here, and then divide by the standard deviation. And the test statistic that we're getting is minus 2.34. And we're able to calculate the we're able to calculate the test statistic and then the probability, the p-value for this test statistic, which is very low. It's 0.009, so it's really quite significant. So that's how we calculate this manually. We're then able to also follow up and just look at how this might be able to be calculated using the automated approach. You can ignore the W value here, it's not necessary. And the p-value is broadly in the same range. It's definitely significant. So that's how you would do it using the inbuilt R function. So let's move on now to the matched pairs difference test. So imagine in the same data set, we basically have data for poverty by state for different years. So we have the year 2000 and we have the year 2010. And you'll remember from the previous lab, I spoke just very briefly about the global financial crisis between 2007 and 2008. And that had many impacts for the next couple of years. Actually, the economy took really quite a major hit, particularly in the Western nations like the US. And this was all linked to the subprime mortgage issue, which we discussed in the previous lecture when we focused on the number of homeowners who were underwater, so in negative equity essentially. Part of this example here is basically recognizing the fact that because of this financial crisis and the macroeconomy taking a fairly substantial downward trend, the poverty rate consequently is expected to increase during that time. So what we're interested in doing is testing whether this hypothesized increase is actually true. So what we want to do is we want to save the data for the two different years of interest. So let's take the year 2000 and the year 2010, and let's allocate those columns that we have to their own variables. So poverty rate 0 and poverty 10. And then we can find the summary of these variables. So just looking at the poverty rate in 2000, the mean was about 10.87%, whereas in 2010, the actual mean poverty rate had increased almost by 50%. It's at 14.26%. So it's quite a substantial poverty rate increase. And if you look at how these poverty rates are actually distributed, it's quite interesting. That's really quite nicely distributed in terms of the normal distribution, the bell-shaped curve, and actually it's also quite nicely distributed as well for the 2010 data. So that provides us with a bit of an overview of the context. What exactly are the hypotheses? Well, the null hypothesis would be that essentially the mean from 2010 and the mean from 2000 would essentially be the same, so they're equal. Whereas the alternative hypothesis is that the poverty rate has increased in 2010 against 2000. Okay, so x bar 2010 is larger than x bar 2000 because we would expect poverty rates to increase when there's a major global recession. Then we need to define the test. Obviously, this is a matched pairs test because we are taking data rates for the same underlying entities. So these aren't independent samples, it's a dependent sample. It's the same entities having been sampled at a second point in time. So we need to then get the stats required in order for us to do this. So essentially we need to get the length of the different vectors that we've got, which is 51, so one for each state. We then need to get the mean, so x bar 1 and x bar 2 for the different poverty rates, which are listed as 14.26 for 2010 and 10.87 for 2000. And then we want to get D, so we want to get the difference between, so we want to get the differences between the two vectors. So what this is doing is it's subtracting the 2000 values from the 2010 values. And remember, if you have the two vectors going downwards like columns, you're subtracting each individual data points in each row from the other one. So I hope that's clear. Let me just show you what I mean by that. Imagine you had it's just basically subtracting from the opposite value that you have, like this. So imagine this is so these are the different vectors. It's just from each cell or each place has the value taken from the same place in the other vector. Okay. So I hope that that's clear. And actually, let's just get up the equation that we use to do the matched pairs test. So this is what we are interested in. what we just got there was the difference for the matched pair I. So you could call this xi and yi there, and then essentially what we would end up here is di. Okay, so we get those differences. Now we need to choose our significance level. We're going to go for the 95% confidence level again, so we want to be 95% sure that the results haven't just occurred by random. We then need to get the number of degrees of freedom for this test. So number of degrees of freedom is always the number of data points you have in your sample minus 1. And I gave you that analogy last week where I was explaining about how you can think of the number of degrees of freedom as allocating players onto a soccer field. And essentially, once you've allocated the first 10 positions to new players out on the field, the last player has to take the goalkeeper position, and there's no other position for that person to go to, essentially. And that means that final person doesn't have a degree of freedom. So every player before that had a degree of freedom. So if you have 11 people on a soccer pitch on one team, then you would have 10 degrees of freedom. Okay, so it's the same concept here, just for this particular example. So n1 minus 1, 50 degrees of freedom in this case. And we need to delineate the regions of the region of rejection. So we've been through this many times before. So the reason why I'm doing this now graphically is so that you can see exactly what we mean by the rejection region, which here is highlighted in red. I think the important point to emphasize is that we think the poverty rate has increased. So this is a directional hypothesis. We're going to be looking just to see whether that the value that we get sits in the upper tail of the distribution, so in the red zone essentially. So this is the point of interest. The t critical value, in case you are interested, is 1.67, 1.68 after rounding. So that's going to be useful for later. And then what we can do is we can get the d bar, which in this case we're subtracting the two means from each other to get the d bar, as per the equations on page 141 and 143 within the book. And then essentially what we're able to do is we're able to get the standard error. So I'm just looking at the equation here. So this is the standard error of the mean difference. And you can see here if I just run this code. Oh, my apologies. There we go, we're getting a value of 0.3. And essentially this looks like a really big, scary equation, but it's not that different from what we've been doing in previous examples to calculate, for example, the standard deviation. So what you've got is the sum of the differences squared here is the numerator, and then you've got n times the number of degrees of freedom down here, and there's the numerator, the denominator, and then we take the square root. So essentially we end up with this sigma d value here. And we're able to show that to get the t statistic. So it's d bar divided by the SE, the standard error. So the mean of the matched pairs divided by the standard error of the mean difference. And actually we get a really large difference here. I mean, that's a t statistic of 11, so it's not even on the area that we plotted on our region of rejection down here in the right hand corner. So we only had up to 4 standard deviations above the mean plotted in this area. So for 11 to come out, you know, that's highly significant, which is suggesting overall that we have sufficient evidence to reject the null hypothesis at the 95% confidence level. We can actually get the p-value for that, which is really quite small. So it's 2.81 to the minus 15. So it's very small. But we can just have a look at how we calculate that using the inbuilt function, and we can see that the p-value using the t-test approach at the 95% confidence level is broadly similar. Great, so let's just move on now to the non-parametric Wilcoxon matched pairs signed rank test. And essentially, we're just using the same variables as we used in the last test to do the inbuilt calculation here, which lets us compare the match pairs from a random sample for the difference. And when we do that for the poverty rate in 2010, poverty rate in 2000, we end up with this really quite small p-value, again to 7.2 to the minus 10. So even if we use the non-parametric version here, after downgrading the continuous data to ordinal, this is highly significant. So it's a very, very strong effect that we're able to capture. Okay, I think just in terms of the interpretation here, it's just important to emphasize that we get a test statistic that we don't deal with in this class, but it reports the value down here, so the v value. We're not covering it right now, so the important thing was just to emphasize the p-value that we got, which I think we've covered now. Okay, so let's move on to the two sample difference of proportions test, and this is going to be the last one that I cover today within this lab. So this is an example from page 165 and 168 in the book. Let me just open that up. 65. Great, so you should all have seen this now. You've got the different obesity levels for each of the states. You can run the code here, and then you can also read through the example that's in the book as well. I think that will help reinforce your understanding. In this particular case, we're looking at obesity levels in Alabama in 2000 and then again in 2010. And we want to see if the proportion of Alabama's adult population classified as obese has increased significantly between these two data points, so between the turn of the millennium and then 2010. So the obesity level for adults in Alabama, essentially, it was about 23.9% in 2000, but then by 2010 it was about 32.8%, so it's increased really quite significantly by about 8.9%. So let's just enter these ratios enter the data to get the ratio first. So imagine that there were 2,156 people sampled in 2000, and then 516 of these people are ranked as obese. That basically provides us with this this rate of about 23.9% for the year 2000 for Alabama. And then for the year 2010, the number of people sampled was about 7,269. And then essentially about 2,388 were actually ranked as obese, quite a large number. And that equates to about 32.8% of the state population that are classed in this weight category. So we need to now define our significance levels. So we want to be 95% confident that the results don't occur just by chance. So we want an alpha level of 0.05. So we would expect the p-value to be lower than this in order for us to reject the null hypothesis. And what we need to do is we need to set up the data for the proportion test. So we need a vector for both the x values and a vector for the n values. So essentially, when we input those into the global environment, we've got the x and the n vectors that are ready essentially for us to calculate the statistics for. In fact, I'm just going to clear the environment so that we've got this in a more succinct fashion. There we go. So now we've got the x vector here and the n vector. Great. And now I'm going to actually run this test. So for example, we're going to use the inbuilt prop test that you're able to read up on the background of this particular function. If you aren't familiar with it, you can type the usual help entry and go into the R help menu to get that information. and then you can actually run it. So we're placing in the x and the n vectors, we're focusing on the greater proportion, we're giving the confidence level, and essentially what we end up with is a chi-squared value, which we will cover actually later in the term. We're going to be covering chi-squared as its own specific test. But the important thing here is that if we take the square root of the chi-squared, which so it's 62.043 is the chi-squared value. If we take the square root of it, then we're able to get the z value, which is about 7.87 here. So it's really quite a large z value, which is giving us pretty much 100% confidence that the values are significantly different. Okay, so we can see from the built-in test that our p-value is essentially 0.00, so the p-value here is 1.68 to the minus 15, so it's very, very small, which tells us that the proportion of Alabama's adult population classified as obese has significantly increased between those two sample periods of the turn of the millennium, the year 2000, and then 2010. And that basically provides us with a very, very strong degree of confidence that this particular conclusion is true, because you know, this value would even exceed a 99.9% confidence value, for example, if that's what we decided we wanted to use. So an alpha of 0.001. Okay, great. Well, that is all that I'm going to cover today in the laboratory. So I hope that that was clear to you and that you've been over all of these different tests. We've covered quite a few, and we've both worked out how to do that manually. So I hope that that supplements some of those calculations that we did manually in the spreadsheets in the lecture, as well as the theoretical context. And then we've actually calculated them automatically using the inbuilt R functions that allow us just to do these tests very, very quickly. So cover this material, read the chapter, make sure you go over that, have a go at the assessment. If you've got any queries or questions, or you want to reach out to me, then please do. It'd be nice to hear from you. And I hope you have a good week, and I hope the work goes okay, and let me know how you're getting on. Thank you very much for tuning in, and I'll see you soon. Goodbye.